Hello everybody. Today we're going to talk about polar coordinates. A coordinate system represents a point in the plane by an ordered pair of numbers called coordinates. Usually we use the Cartesian coordinates, which are directed distances from two perpendicular axes. This is when we're dealing with the xy plane. Here we describe a coordinate system introduced by Newton, and this is called the polar coordinate system, which is quite convenient. We choose a point in the plane that is called a pole or an origin, and it is labeled as the letter O. Then we draw a ray or a half line starting at the origin called the polar axis. So in this picture to the right, you can see that we have the polar axis here along with the origin. So our origin is where the O is, and then the polar axis is that horizontal axis, very similar to your x-axis. So this axis is usually drawn horizontally to the right and corresponds to the x-axis in the Cartesian coordinates. If P is any other point in the plane, let R be the distance from the origin to point P, and let theta be the angle, usually measured in radians, between the polar axis and the line OP. So here's any other point P. Notice that it has coordinates R and theta. And the theta, again, is measuring this angle. And the R is measuring the distance from the origin to the point. The point P is represented by the ordered pair r theta, and r and theta are called polar coordinates of P. We use the convention that an angle is positive if measured in the counterclockwise direction from the polar axis and negative in the clockwise direction. If P is equal to O, then R is equal to O. In other words, if your point P is located at the origin, then your R is equal to 0. And we agree that 0 theta would represent the pole for any value of theta. We extend the meaning of the polar coordinates r theta to the case in which r is negative by agreeing that, as in figure 2, the points negative r theta and r theta lie on the same line through the origin at the same distance, the absolute value of r, from the origin, but on opposite sides of the origin. So if you have r theta, like we have up in the upper right, that's in the positive direction of r, and then we have negative r, which would be in the opposite direction. So same line, same distance, just opposite directions. And the difference between those is an angle of pi, so a straight line angle pi. If r is greater than 0, then the point r theta lies in the same quadrant as the angle theta. If the r is negative, then it lies in the quadrant on the opposite side of the pole. Notice that negative r theta represents the same point as r, which would be the original r value, the original theta value plus pi, which is what I was just mentioning. Because of pi being a straight line, 180 degrees, that would give us the opposite side of the line. So in example 1, what we're going to do is get used to polar coordinates by trying to plot them on the polar coordinate plane. So we have these polar coordinates, 1 and the angle 5 pi over 4, 2 and the angle 3 pi, and so forth. And we're going to take a moment and plot these on the polar coordinate system. So notice that for the first point, A, we have a radius of 1. And if you look at the polar axis, they're kind of labeled as how far the radius would be. So there's a 1, 2, 3, and 4, and each distance represents a different radius, or r. So here we have 1 would be the first circle all the way around, 2 would be the second circle all the way around, and so forth. So if we're trying to find 1, 5 pi over 4, we're going to use this first circle for our radius there, and then for 5 pi over 4, we're going to find the angle 5 pi over 4 in the counterclockwise direction. So there's 5 pi over 4 with a radius of 1, and we're going to plot our point right here. So our first point we're going to label as A, with a radius of 1 at the angle 5 pi over 4. Okay, the next one is going to be the point 2, 3 pi. Now we know that 2 pi is 1 full revolution around the polar system. So another half revolution would get us to 3 pi. So 3 pi and pi would go together. And then we would need to have a radius of 2. So that'd be the second circle out. So there's my radius of 2. And I'm going to label that as point B. Okay. The third one is going to be 2 and negative 2 pi over 3. Now remember that, our radius, of course, is 2, and our angle on this one is negative 2 pi over 3. Okay, but because it's a negative angle, we're actually going in the clockwise, direction. So instead of going counterclockwise, we're going to be going the opposite way. So we're going to be going down. And so we need to go down negative 2/3. Now negative 2/3 would be the same as 4 pi over 3. So this is negative 2 pi over 3, which would be the same there. And then our radius is not negative, it's positive, so we would still be using this same line here, and we'd go to the 2. So 2 would be right there, and we'll label that as point C. Okay, the last one here is when we have a negative r. So remember, that means you're going on the opposite side of the line, and we're using the angle 3 pi over 4. So we'll be going in the counterclockwise direction on this one, but just remember we're using the opposite side of the line, when we actually plot our point. So let's find the angle of 3 pi over 4. So 3 pi over 4 would be way over here, and then 3 would typically be, 3 circles out, 1, 2, 3, but we're going in the opposite direction. So you actually want to go 3 circles in the opposite side of that line. So 1, 2, 3 would actually put us right over here. So we're going to plot our point right there, and we'll label that point D. So hopefully this little practice helped you kind of understand the idea of negative r values, negative angle values, and then how to use your r and your angle to plot the point as a whole. Now, the connection between polar and Cartesian coordinates is shown on the right. So what we have here is a polar coordinate, r theta, and its point is right here on the system. And if we were to drop a vertical down to the polar axis, which coincides with the x-axis, we would get a horizontal and vertical distance, which represents the Cartesian plane. So the way to connect this is to use that right triangle. Notice by dropping that line down, we have this right triangle here. So we're going to use some right triangle trig to help us figure out how to change from polar to Cartesian and Cartesian back to polar. So we have our vertical distance y or horizontal distance x, and then our hypotenuse would be our distance r. So connecting those, let's first write that according to the angle that we have here, theta, x would be the adjacent side, y would be the opposite side, and r would be our hypotenuse. So using some of that right triangle trig that we know, if we have some point P and we want to connect them using Cartesian and polar, the idea is to use that right triangle trig. So cosine is adjacent over hypotenuse. So we would have x over r. So the cosine of theta would be x over r, and the sine of theta would be our opposite over r, our hypotenuse, so y over r. So using that, you could multiply both sides by r here, and by doing so, you would result in the equations in this box. So if you want to figure out what the x value is, you would do r times the cosine of theta. If you want to figure out what the y is, it'd be r times the sine of theta. Now, to find the r and theta when you know your x and y, so let's say you're starting with Cartesian and you want to change it to polar, you're still going to use that right triangle idea, but now we're going to connect it slightly differently. One of the ideas is you're going to use the Pythagorean theorem, and the other is to use tangent this time. So tangent is opposite over adjacent, so that'd be y over x. And then you can use the Pythagorean theorem to also help you solve for your r value as well. So what we're going to do in example 2 is use some of these ideas to answer and convert from one to the other. So in example 2, it says to convert the point 2, pi over 3 from polar to Cartesian coordinates. So to start, we know that we have an r value of 2 and an angle of pi over 3. So what we need to do to change this to Cartesian, which again is x and y, is to use the two equations above. X equals r cosine theta and y equals r sine theta. This, if we create these equations, will give us the x and y values. So I'll start with x. So x is equal to r cosine theta. So x in this case would be equal to 2 times the cosine of pi over 3. So the cosine of pi over 3, and I'm sure with this unit with this lesson, you'll really start to remember your unit circle. So cosine at pi over 3 is 1/2. So 1/2 times 2 would give us an x value of 1. Now we'll do the same to find our y. Y is equal to r sine of theta. So plugging in what we know, y is equal to 2 times the sine of pi over 3. And again, using the idea of your unit circle, the sine at pi over 3 is root 3 over 2. So y would equal root 3 when we simplify. So the ordered pair would be 1, root 3. And that would be in Cartesian coordinates x, y. Okay, let's look at number 3. Number 3 is going in the opposite direction. It's starting with Cartesian, and it's asking us to go to polar. So the first one is the Cartesian point x, which is 1, y, which is -1. So one of the best things to do with this one is to plot the point first so you know what quadrant you're in. So if I were to just really quickly kind of get the idea of where 1, -1 is, that would be down here in the 4th quadrant. So quadrant 4. And the reason you want to do that is when you're dealing with angles for your theta, when you go into polar, it's nice to know what quadrant you're in because sometimes you need that as a reference. So the two equations that we'll use to help us are the Pythagorean theorem one, r squared equals x squared plus y squared, and then the tangent, which is tangent of theta is equal to y over x. So we'll start with our r to determine what our r value is. And we'll again just write down that equation, x squared plus y squared equals r squared. And we'll plug in what we know. So we know that x is 1. We know that y is -1. And we're using this to determine what our r value is. So 1, of course, squared is 1. -1 squared is 1. And that's equal to r squared. So this is letting us know that the r is equal to the square root of 2. Now, the theta is the next thing we need to solve for, the angle. And for that, we'll use the tangent. Okay? So I'm just going to write it as the tangent of alpha, giving it a different variable at the moment. And we're going to set it equal to, remember, it's y over x. Okay? So tangent of alpha in this case would be equal to -1 over 1, which is really just -1. Now we need to do inverse tangent, or arctangent. And remember, this question is asking us, at what angle does tangent equal -1? And you might put that in as -pi over 4. But we want to try and measure this using positive angle measures if you can, which is why I labeled this angle as alpha, because the theta is the final answer angle. So we have to think to ourselves, okay, so -pi over 4 is going is going clockwise. We want to figure out what its corresponding angle is going clockwise. So what would that be? And that would be the angle 7pi over 4. So we'd have a radius of positive √2, and the reason it's positive √2 and not negative √2 is because I'm measuring from the origin out in that positive direction. If I were going in the negative direction, I would be up here in the second quadrant, right? And then I would need this to be in the fourth quadrant, so it would need to be a positive. And then we found our arctan as -pi over 4, and then found its corresponding angle, which would be 7pi over 4. So this answer, if we were to write it as an ordered pair, would be √2 7pi over 4. So using those same ideas for part B, we have the ordered pair 5√3, 5 for our x and y values. Again, it is suggested that you try to determine what quadrant that would be in first. So 5√3 is positive, and then 5 is positive, so that would be in the first quadrant. So we're going to write quadrant 1 as a reminder to ourselves so that when we get our final r and theta, we know that we're using the proper r and angle measurements. Okay, so using the same ideas as we did before, we're going to need to use the Pythagorean theorem and the tangent to determine our r and theta. So what I've done is set up our first one for our r value, and it would be our x value squared plus our y value squared is equal to our r value squared. So squaring this first one, we would get 25 from the 5 squared, and we would get 3 from the square root of 3 squared. And 25 times 3 is 75. So this first term would be 75. The second term would be 25, and that would equal r squared. So together we would have 100 is equal to r squared, which is telling us that our r value is really 10. So our radius is 10. Now we need to use our theta equation to help us solve for the angle. So the tangent of alpha is equal to our y value over our x value. This, of course, can simplify to 1 over √3. And so we need to take the arctangent of that. So inverse tan of 1 over √3. And again, that question you need to ask yourself is, at what angle does tangent equal 1 over √3? And that is at the angle pi over 6. Now, before we label that as our theta, we need to remember, is pi over 6 going to be in quadrant 1? And the answer is yes. So we can just go ahead and rewrite pi over 6 right up there. So our ordered pair for this one should be 10 pi over 6. Okay. Now for example 4, we're going to take actual equations and convert them to polar equations. So this first equation here is x squared plus y squared equals 25. And this type of equation probably looks familiar to you, and we'll discuss what it is in just a moment. The second equation is 2x minus y equals 5. And again, this should look relatively familiar to you as well. So what we're going to do is take these equations, which are currently in terms of x and y, and we're going to convert them to polar, which means that they'll be in terms of r and theta. You're going to use the same equations that you used above to assist you with this process. So in this first one, we're going to use the equation x equals r cosine theta and y is equal to r sine theta. And we can actually replace the x and the y values in this equation with r cosine and r sine respectively. So the first one would become r cosine theta squared, and the second would become r sine of theta squared, and that would equal 25. So all we did is replace the x and the y with r cosine and r sine, depending upon whether the variable was x or y. So now we can simplify this a little bit. Because the r and the cosine and the r and the sine are multiplying, you can distribute this exponent of a 2. So that's going to become r squared cosine squared plus r squared sine squared, and it's still going to equal 25. At this point, you can factor out an r squared, and you'll have cosine squared plus sine squared remaining. This probably looks familiar to you because the cosine squared and the sine squared is an identity, and we know that that's equal to 1. So really, instead of r squared timesing with the cosine plus sine, it's really multiplying with a 1 as well. So we can just write that as r squared is equal to 25, which would mean that r is equal to 5 when you take the square root of both sides. So there's our first equation. Our second is still going to use those same ideas, knowing that x is equal to r cosine theta and y is equal to r sine theta. And again, we're just going to replace the x and the y using these two equations. So 2 times r cosine of theta minus r sine of theta is equal to 5. The idea here is to try to be able to solve for r. So we can factor out an r from both of these pieces. So r would come on the outside, and we get 2 cosine theta minus sine theta. That's equal to 5. And then we can actually divide by what's in the parentheses. And that would allow us to solve for r. So our final equation here would be 5 divided by 2 cosine theta minus sine theta, and that would be our equation in polar coordinates. Now, the two sentences on the bottom here I think are kind of interesting. So the polar equation for a circle is much simpler in polar coordinates than in rectangular or Cartesian coordinates. So notice this equation that I mentioned earlier, this was our equation for a circle. And in Cartesian coordinates, it's x squared plus y squared equals your radius squared. In polar coordinates, it's just r equals 5. So I think that's kind of interesting to see how much simpler it is in polar coordinates. So the second one is an equation of a line. right? So this one is an equation of a line here. And so that's 2x minus y equals 5. We, of course, could solve that for y equals mx plus b, or just leave it in this form. But this equation that we have here, 5 divided by 2 cosine minus sine, is much more complicated for a line in polar than it is in Cartesian or rectangular. So it's just interesting to see the comparison of how sometimes it will be simpler in polar and sometimes it won't, and vice versa for rectangular as well. Now, for example 5, we're still going to be converting this to the other form from polar to rectangular. However, we're going to have to use an extra idea that we haven't used in the first two examples of converting equations. So we're still going to use those two equations that we have, our cosine of theta and our sine of theta. But now we're going to actually use the Pythagorean theorem one, which is the r squared equals x squared plus y squared. And for this, it doesn't look like you have the r squared ability in this, but we can actually manipulate this equation that we're working with a little bit in order to use that r squared. So what we'll start with is just writing the equation down. R equals negative 3 cosine theta minus sine theta. And what we can do is multiply through everything with the variable r. And by doing that, it makes our first term here r squared, and then it also makes us have the r cosine theta and the r sine theta to help us with those two equations. So the r squared can be replaced with the x squared plus y, and the x squared plus y squared, excuse me. We'll still have that negative 3. The r cosine can be replaced, of course, with x, and the r sine can be replaced with y. So we've replaced 3 pieces of the equation with their corresponding parts. So now we have x squared plus y squared equals negative 3x minus y. And so we can actually leave the equation in this form since it might not be so simple to solve in any other way. And now we have changed it from polar to rectangular form. So that is the same equation written in a different form. Now let's talk about polar curves. We're going to actually learn how to graph on the polar system. So the graph of a polar equation, r equals f of theta, or more generally, f of r comma theta equals 0, consists of all points that have at least one polar representation, r theta, whose coordinates satisfy the equation. So let's start with example 6. It's actually not as complicated as it sounds. Example 6 is kind of fun because, and I know that sounds silly, something is fun, right? But here we have the equation r equals 2. And this is saying that r is always equal to 2. And it's saying what curve is represented by the polar equation r equals 2. Well, if you remember before when we converted an equation and we got r equals 5, we said that that was an equation of a circle above in example 4a. And so we knew that this was the equation of a circle. So r is equals 5 is a circle. So guess what this curve is also going to be? A circle. But its radius is going to be 2. So if we were to graph this equation would actually look like, if I can actually draw a circle, it's a little challenging, apparently. It's just going to go all the way around that circle for radius 2. So that would be what this graph looks like. R equals 2 is a nice circle with radius 2. Now, of course, they're not all going to be that simple. Examples 7 through, I think, 12 are going to require us to do a little bit more thinking and planning ahead in order to graph them. Now, for example 7, 8, and so forth, you're going to have to remember that we're dealing with periodic graphs, so sine and cosine, And I want you to think back to dealing with transformations. So the amplitudes of the graphs, the periods of the graphs, whether they're shifting up and down and so forth. So for example 7, this is the sine function, but it's having 1 added to it. So for this, we're actually shifting the graph up 1. And that will help you kind of get the general idea of what's happening. So all we're going to do is take the sine function and shift it up 1. So normally we'd start at 0, so now we're starting at 1. And then at pi over 2, normally we would be at 1, but now we're going to be at 2. Okay, so once you get the general shape of the graph here, using the idea of the sine function being shifted up 1, you can kind of graph and connect your points. I want you to relate this back to r and theta. So this first point here, when we evaluate this r function at the angle 0, my radius would be 1 and my angle would be 0. At the second point here, it would be a radius of 2 and an angle of pi over 2. This third point would have a radius of 1 and an angle of pi. This fourth point would have a radius of 0 and an angle of 3 pi over 2. And this last point would have a radius of 1 and an angle of 2 pi. So notice I'm getting the angle from where the point is on the axis there, and I'm getting the radius from how high that curve is at that point. Okay, so my radius for the first one is 1 and my angle is 0. So what I can do is take that point and plot it on the coordinate or in the polar system by plotting the point r equals 1, theta equals 0. So at angle 0, which is right on the polar axis, it's going to have a radius of 1. So I'm going to plot that point. Then I'll plot the next one, which is r equals 2, theta equals pi over 2. So at pi over 2, I'm going to plot a radius of 2. And then at the angle pi, I'm going to plot a radius of 1. And then at 3 pi over 2, I'll plot a 0. So that takes us back to the origin. And then back at 2 pi, we have a radius of 1 again. So that takes us right back where we started. So what this is going to look like is it's going to flow out and back, and then flip inside, and then back out again. So it's kind of following this flow here. Okay, it almost looks like an upside down heart in a way. So we're starting at theta equals 0, and we're ending at theta equals 2 pi. And so you can see that plotting it first on this plane and determining what each point would be, and then taking those points and plotting them on the polar plane or on the polar system makes it a little bit easier. Now, of course, you can do this with a calculator to make sure that you're correct. So first, turn your calculator on and change your mode. So far in our calculator, we've done function mode, parametric mode. So now we're going to go to polar mode, P-O-L, and hit enter. Now we're going to go to y equals, and we're going to type in the equation as we have here, r equals 1 plus sine theta. So 1 plus sine, and then when you hit your variable button, it'll automatically come up with the theta. And then close your parentheses. So now let's see if we can get our window correct. So let's go to our window. Doing from 0 to 2 pi is a good idea. So theta min can be 0, Theta max can be that 2 pi, which is what we have there. You can, of course, change your step value. This is what was automatically there when I started. You could change that if you wanted, but I think I'll just leave it as that. So then we can go down to x min and x max. Now notice my R values are not very large, so you could, of course, make this smaller. Instead of at -10 to 10, you could make this smaller, maybe -5 to 5, and that might zoom in on the picture a little bit to help give it a closer view. So now if I go ahead and hit graph, we can see that we kind of have the same shape. Now, if I were to maybe zoom in a little more, maybe -3 to 3, it might give us a little bit more clear of a picture. And also if I were to square up my picture here, my graph, that might help make it a little clearer as well. So there we can kind of see that we have the same general shape. It comes out a little bit at the bottom here. It goes up to this high point and it kind of curves its way around. So that's how you can use your calculator to kind of double check to make sure what you're doing on your paper is accurate. Now let's look at example 8. Again, I want you to think about those transformations. So this number in front here, this 3, is changing our amplitude. So my amplitude is now a 3. And this 2 theta here is changing your period. So your period is now going to be divided by 2. Okay, so let's take the general shape of the sine function and change it using this amplitude and this period. So sine at 0 is still going to be 0, even with a different period. So that's still going to be 0, and timesing it by 3, our amplitude is going to keep it at 0. So our first point here is going to stay the same. Now at pi over 4, the sine function, or excuse me, normally at pi over 2, the sine function would have a value of 1. But remember, we're dividing our period in half. So instead of having that 1 at pi over 2, it's actually going to occur at pi over 4. So halfway between 0 and pi over 2. So our period is changing our curve and kind of making it a little more condensed. And so it should have a y value of 1 there, but now we're going to multiply that by 3 for our amplitude. So instead of having a y value of 1, it's going to have a y value of 3. So we're going to amp it up. Okay, now normally the sine curve would be back at 0 at pi, but remember it's being cut in half there, so it's going to be at pi over 2. So it's going to be back at 0. And then we are going to kind of follow this pattern. So we're basically going by every quarter pi. It's going to go between 0 and 1. Now at 3 pi over 4 here, which would be halfway between pi over 2 and pi, instead of having an amplitude or a height of 3, it's going to be at -3, because normally it would go down to -1, the sine function. So now it's going to go to -3. So you can kind of see how the sine function is getting much taller because of the amplitude, and it's much more condensed because of the period. So I'm just going to kind of finish this curve out here. So then it's going to go to pi and then back at 1 at this quarter value here, and it's just going to kind of follow this curve all the way to the end. And so what I'm going to do is draw this and connect my points so I can kind of see what's happening on the rectangular coordinate system here. And then I'm going to write my R value and my theta values next to each of these important points so that I know what to plot on my polar system. So to start, this first point would have an R value of 0 and an angle of 0 as well. The second one would have a radius of 3 and an angle of pi over 4. This third one would have a radius of 0 and an angle of pi over 2. And then you just are going to keep going all the way to the end, labeling each important point with a radius or your R and your angle measure. So I've labeled each of the important points. Now I'm going to take those points and plot them on the polar system. So the first one I'm going to start with is R equals 0, theta equals 0, which would be right at our origin. And then I'm going to have R equals 3 at pi over 4. So pi over 4 is in this first quadrant here, so it's going to have a radius of 3, and then it's going to kind of come out to that point, and it's coming in that direction. Okay, so it's coming out towards 3. Then it's going to go back towards a radius of 0 at pi over 2. So at pi over 2, we're back at the origin. So it's kind of coming back. So we kind of created this little leaf almost, or petal. Now we're going to go to 3 pi over 4. So 3 pi over 4 is right over here on the left, but remember we're doing a negative radius, so remember it's on the opposite side of that line. So a negative radius would actually be over here. So I'm going to bring that out with an arrow, and then it comes back to a radius of 0 at the angle pi. So right back to the origin. And then it goes to a radius of 3 at 5 pi over 4. So at 5 pi over 4, which is down here on the left, so down at the left, we're going to have a radius of 3, and that's a positive radius, so it would come right back out. And then it's going back to the origin at 3 pi over 2. So at 3 pi over 2, it's back to the origin, so right back there, going back in. And then at 7 pi over 4, which is down on the right, it has a negative radius. So it's not going to be plotted on this side. It's going to be plotted on the opposite side of the line. So now it's coming back out. And then again, radius of 0 at 2 pi. So it comes right back in. So what we kind of created is this little 4-petal flower, if you will, or 4-petal clover. And this pattern is just going to kind of repeat as we were to continue down, with further angle measures. So it's kind of neat how these graphs play out, and you can of course check this on your calculator. So if I were to put our equation 3 sine of 2 theta into our calculator, and I already had my window set up before from 0 to 2 pi. I just kept the original step value for our theta, and then I just kept negative 3 to 3. I could certainly change that since my amplitude is 3, so maybe like negative 5 to 5. So I can certainly change this as I see fit. And now if I go ahead and hit graph, you can see how this actually does follow the graph that we have here. And you can trace it if you want. You can start and go ahead and trace it, and it'll kind of show you how the graph flows, just like it did with parametric, how the general flow of the curve goes from 0 to 2 pi, since that's what we have our theta calculated for. So that's a neat thing to check with your calculator, and it also always looks nice on the calculator. Okay, so for this question, number 11 is what we're going to skip to. This is going to be the last one that we do today. We're going to sketch the curve r equals 4 cosine of 3 theta. And I wanted to do this one because we haven't done a cosine one yet, so we might as well do one of those. But again, you still want to think about the idea of transformations. So this 4 in front is going to affect your amplitude. So my amplitude is now going to be 4. This 3 inside the cosine function is going to affect my period, and that means that my period is going to be divided by 3. So when things normally would happen, the big things for cosine would typically happen at pi over 2 pi, 3 pi over 2, and 2 pi, alternating between zeros, ones, and negative ones. It's going to happen faster now because we're dividing our period by 3. So let's go ahead and see if we can sketch this. So on our XY plane first, and then we'll convert it to r and theta, and then put it on the polar plane. So normally cosine starts at 1 at angle 0. So because the amplitude is now 4, it's going to bump up to 4. Okay, then cosine would normally be 0 at pi over 2, but because the period is being divided by 3, it's actually going to be at pi over 6. So it's actually down at pi over 6 now when it's 0. And then at pi over 3, instead of, it being back to -1 at pi, it's going to be -1 at pi over 3, which is right here, but because the amplitude is 4, it's going to be down at -4. So we're going to be down here, and then we'll be back kind of following that pattern. So it's going to go back to 0, and then back to +4, and then back to 0, and then back to -4, and then back to 0. So as you can see, the pattern just continues. Okay, so here's the general picture of what we have going on, the general graph. Don't mind the wobbly lines. So what we're going to do now is take each of these important points and label them with their R and angle measurements. So R in this first one is going to be 4, and the angle is 0. In this second one here, R is 0, and our angle is pi over 6. This one down here, R is equal to -4, and our angle is pi over 3. And then this one right here, this fourth point, R is equal to 0, and our angle is pi over 2. So take a moment and finish labeling each of these points. So I've labeled each of the points with the R and the theta that corresponds to it. And now I'm going to take a moment and plot that on our polar system. So the first point I'm going to plot is R equals 4, theta equals 0. So this is going to actually fall on our polar axis here. Angle measure of 0 and radius or R of 4. So that'll leave us right there. That's our starting point. And then it's going to go to 0 for our radius at pi over 6. So our next point is at pi over 6, and we're going to go to 0. Okay, so it's going to flow like that. And then after pi over 6 is pi over 3. So we have the value at -4. So here's pi over 3, but remember the R is negative, so it goes in the opposite direction. So it should be -3, or excuse me, -4. Our radius is -4 this time, not 3's. So I'm going to continue just kind of drawing that out. So it's kind of flowing out this direction now. And then after pi over 3, at pi over 2, it's back to the origin. So it just kind of flows right back. And you can see that we're creating those petals again. And then at 2 pi over 3, we have a radius of 4. So 2 pi over 3 is up here in the left, and it's going to have a radius of 4. So it kind of flows out in this direction. And then after 2 pi over 3, it goes back to 0 at 5 pi over 6. So 5 pi over 6, it's just going right on back. And then after 5 pi over 6, it's going to be at the angle pi, which is right over here on the left. And then it's going to have a negative radius. So remember, it's on the opposite side. So this actually brings us back to where we started. So this is 3 lovely petals. Now, if I were to continue plotting points, this second half of this information that we have up here, if I were to continue using it, it would take me right over top of where we already plotted. So we just finished at R equals -4 pi for our angle measure. So if I were to go right back to 7 pi over 6, which would be the next point, so 7 pi over 6 is right here, okay, it would bring us right back to 0, okay, to our origin. And then after 7 pi over 6, it'd take us back to a radius of 4 at 4 pi over 3. So 4 pi over 3 is right out here. So notice that it's taking us right back to where we've already been, which is right out here. So it's just going to retrace its steps, so to speak. And if I were to continue, extending all these angle measures out and finding all the corresponding R values, it would continue retracing. So this is the shape of the graph, and we can actually see this on the calculator. So here's our calculator. Here's our original function, r equals 4 cosine of 3 theta, which is what I've typed in here. I have the windows set up from -5 to 5 and from 0 to 2 pi. I kept the steps the same as what they were defaulted to. And if I just go ahead and hit graph, I see that I get that 3-petal flower, which is what we have on our own polar system. But if I were to trace it, remember I set this window up from 0 to 2 pi, so I should start to see that retracing happen once we get to the ending point of pi. So that full 3-petal flower happened from 0 to pi. And so once I get to pi and continue onward, I should cease to see the retracing happen. So I'm going to go ahead and hit trace, and I'm just going to hit arrow to the right, and it's just going to kind of take me on the path of how this was created. So notice it's just taking me down that first petal, taking me to that second petal, bringing me back to the origin, going to that third petal, bringing me back to the origin, and then finishing off that first petal. So remember that was at pi, right? And then here we are. Notice our angle here is 3.14, right? So that's our pi. And now if I were to continue going, it's just taking me down the exact same path that we just went on, continuing all the way until we get to the end, which was 2 pi. So you do see that repeating idea here. So it just starts retracing itself. Okay, and that's what happens sometimes when you have that condensed period and you start to have all these extra points. So at this point, this is what's going to conclude the video for polar coordinates. So hopefully you'll be able to get through some of the graphing ideas, changing from rectangular to polar and polar to rectangular, and then we'll finish up some of these in class.